continue with one example. We solve this example and extract the equation of motion for this system with 2 degrees of freedom. Now we want to find the response for this system for these numerical values. So we need to substitute these numerical values. K is 30, the mass is 5, L is equal to 1, the external force is 0 because we want to obtain the free vibration response, and the initial conditions is considered. The initial displacement x is 0.1, the initial rotation theta is 0.2, and the initial velocity, translational and angular velocity are equal to 0. So for this value, we can substitute and extract the matrix form of the equation of motion. And now we need to solve this equation to obtain the natural frequencies and mode shapes. And finally, we can write the response as a combination of the mode shapes. So the equation of motion for this system, if you substitute the numerical values, will be in this form. This is the equation of motion. As you can see, this is the free vibration for an undamped system with 2 degrees of freedom x and theta, as we consider the x and theta as the generalized coordinate system in this slender rod. So this is the vector for the initial condition, the vector for the initial displacement and initial velocities. We consider the response similar to the single degree of freedom systems. We consider the response in these two harmonic forms with two different amplitudes but with the same frequencies, as you can see, and angle phases, and omega, which are the angle phase and the frequency, and uppercase x and uppercase theta, which are the amplitude of the displacement or amplitude of the response. Now, if you substitute these responses in the equation of motion, we need to calculate the x double dot and theta double dot. You know that the x double dot is minus omega times by x, and theta double dot is equal to minus omega squared times by theta. Sorry, for the first one it's minus omega squared times by x, and for the second one theta is minus omega squared times by theta. So if you substitute here, we will have this matrix M multiplied by minus omega squared plus this matrix K, and all of these terms will be multiplied by the vector x and theta, and must be equal to 0. So this is the equation for after substituting the x and theta. We will have minus omega squared multiplied by x, and for theta double dot we will have minus omega squared times by theta. In the first week, I explained that this is the characteristic for the harmonic motions. If you find the acceleration of a harmonic displacement, the acceleration is equal to minus omega squared times by the harmonic displacement. So here we can factor x and theta from this term, and we can write in the algebraic form, because here we have two algebraic equations, and now we can extract two equations with two unknowns in the matrix form. Okay, so here this is minus omega squared multiplied by matrix M plus matrix K, and all these terms are multiplied by the vector x and theta. So for a non-trivial solution, we know that the determinant of the coefficient matrix, this matrix, must be equal to 0 to extract the characteristic equation. So the determinant of this matrix must be equal to 0. The determinant of this matrix can be obtained. This term, the first column and first row component, must be multiplied second column and second row component minus this component, the first row and second column must be multiplied by the second row and first column, and we can extract the determinant of this matrix. It must be equal to 0. Here you can see we have an algebraic equation from order 4. As I told you, if you substitute omega squared is equal to, for example, alpha, we can extract one algebraic equation from order 2. It will be 1.56 multiplied by alpha squared minus 53.87 times by alpha plus 379, it must be equal to 0. So here you can see we have an algebraic equation from order 2, and you can obtain alpha 1 and alpha 2, which are the two roots for this algebraic equation, by using the delta method. You need to form the delta and obtain the alpha 1 and alpha 2. Okay, so easily you can obtain the frequencies. And once you obtain the alpha 1 and alpha 2, you know that omega, or the natural frequency of your system, the first omega or omega 1 is equal to the square root of alpha 1, and omega 2, or the second natural frequency of your system, is equal to the square root of alpha 2. So from this equation, which is called the frequency equation or characteristic equation for your TDOF, or your 2 degree of freedom system, you can obtain the natural frequencies. And the next step, we can obtain the mode shapes for this equation. So we will have two natural frequencies. Of course, we consider the positive ones. The first natural frequency is 3.14, and the second one is 4.96. So we have two natural frequencies. Now we can substitute into this equation. If we call it equation 1, we use this equation 1 to obtain the mode shapes. So here in this equation 1, if you substitute omega, this is equation 1 in expand form. If you substitute in this equation, which we call it 1, omega is equal to omega 1, which is 3.14, you can obtain the first mode shape. So here you can substitute omega is equal to 3.14. You can see we will have two equations, because 3.14 is the eigenvalue or the natural frequency of your system. These two equations, the first equation and second equation, will give you the same equation. I mean, if you substitute here, you can only obtain one relation between uppercase X and uppercase theta. So if you simplify them, you can extract these two equations. Here you can see from the first one, this component multiplied by uppercase X and this component multiplied by uppercase theta will give you the first equation, this equation. If you simplify, you can extract this form. And the second equation, this component must be multiplied by uppercase X, and this component, the second one, will be multiplied by uppercase theta, and it will give you the second equation. It must be equal to 0, and if you simplify this, you can extract the second equation. From the first one and second one, if you simplify, you can obtain that X is equal to 0.7 times by theta. So because both of these two equations are the same, I mean, from the first equation you can extract that X is equal to 1.524 divided by 2.149 multiplied by theta. So this is the from the first equation, and from the second one, from this equation, you can conclude that x, uppercase x, is equal to 7.1484 divided by 10.1755 times by theta. If you calculate these two fractions, this one or this one, both of them are equal to 0.702. So this value will be obtained from the either first equation or second equation, and you can obtain the in fact the first mode shape from this equation. So from this term you can conclude that x is equal to 0.702 times by theta. So in the mode shape you can substitute, instead of x you can substitute 0.702 times by theta, and instead of theta we can write 1. Okay, so this is the first mode shape. You know that the first mode shape is equal to the amplitude of the x, which is uppercase X, and the amplitude of theta. So if you substitute, instead of x, substitute this term for theta, you substitute here and extract the theta from this vector, you can write the mode shape in this form. Okay, so this is the first mode shape, and now we need to obtain the second mode shape by substituting omega is equal to 4.966. So for this purpose, again in equation 1, we substitute here, you can see we substitute omega is equal to 4.966, and now again we can extract two equations. The first equation is this component multiplied by x, and this component multiplied by theta is equal to 0. This is the first equation. The second equation is this component multiplied by x, and this component multiplied by theta, it must be equal to 0, which results in the second equation. And if you simplify these two equations, if you simplify these parentheses, you can extract these two equations, as you can see, equation 1 and equation 2. Again, from the first equation, from this equation, we can conclude that x is equal to minus 4.63404 divided by 39.152 times by theta. This is the from the first equation. From the second equation, you can conclude that x is equal to, again, minus 0.9909 divided by 8.3264 times by theta. Again, if you simplify these two coefficients, this term or this term, both of them are equal to minus 0.118. So from the second natural frequency, we can conclude that x is equal to minus 0.118 times by theta. So in the second mode shape, which is equal to the vector of the amplitudes x and theta, instead of x, I substitute minus 0.118 times by theta, and also the second component, which is theta. So if you factor the theta and it comes out, so the second mode shape is equal to this term. So we have two mode shapes, and now we can write the response of the free vibration in this form, x and theta, or In the vector form, you can write x and theta are equal to the combination of the first and second mode shape and the first and second natural frequency. Here you can see this is the first mode shape with the first natural frequency, and this is the second mode shape with the second natural frequency for the xt. And for the theta, again we have the first mode shape multiplied by the cosine with the first natural frequency, and the second mode shape multiplied by cosine and this with the second natural frequency. So we will have four unknowns here, phi1 and phi2, and also theta 1 and theta 2. These components will be obtained from the initial conditions, and of course in the exam you are not supposed to solve these equations, because to solve this equation you need to solve a system of four nonlinear equations, and usually we do not expect you to solve this type of equations. Here just to let you know that what is the procedure to obtain these constant coefficients, I show you what is the procedure. And here you can see from the initial condition at t is equal to 0, we know that x is equal to zero point 0.1. At t is equal to 0, theta is equal to 0.2, and at t is equal to 0, the velocities x dot and theta dot must be equal to 0. So here we will have four equations with four unknowns. As you can see in the equations, we have cosine phi1, cosine phi2. Due to these terms, the solution of these equations is a little complicated, and I do not expect you to solve this type of equations. Okay, and generally in the multi-degree of freedom systems, these coefficients are not as important as the natural frequency and the mode shapes. As I told you in the first session, we usually use the mode shapes and natural frequencies to extract the principal coordinate system and to solve these type of systems to obtain the force vibration response and to find a system of uncoupled ordinary differential equations. Okay, so the main application of the mode shapes are there, and also we can find out what is the configuration of the system when it will be excited with, for example, the first natural frequency or second natural frequency. Okay, and finally we can solve this and obtain different sets for the results. But which one can be the solution? It depends on your initial condition. Similar to the procedure in the single degree of freedom systems when we solve for the angle phase and the amplitude. If you remember, we obtained different sets for these constants, and again according to the initial conditions we obtained these constants. Okay, so this is the same, similar to the single degree of freedom systems. The next one is torsional systems. For the torsional system with 2 degree of freedoms, exactly the same procedure is for the solution, only instead of the translational displacement or translational degree of freedom, which is called x, here we will have theta. And instead of the external force F, we will have the moment, similar to the single degree of freedom system. And instead of the linear stiffness for the springs, we will have torsional springs. If you extract the equation of motion for a 2 degree of freedom system with rotational motion, something like this, you can extract by using the Newton's second law. You can extract the equation of motion, as you can see, J1 times by theta 1 double dot, which J1 is the mass moment of inertia for the first mass, and minus KT1, which KT1 is the torsional stiffness for the equivalent spring in the left side of the mass J1, KT2, which is the torsional stiffness for the equivalent spring which is located between the mass J1 and J2, and plus MT1, which MT1 is the external moment which is applied to the mass J1. So here you can see we have 2 degrees of freedoms, theta 1 and theta 2, and again the equation of motion is a system of 2 coupled ordinary differential equations, and we can write it in the matrix form. In the matrix form, you can see we will have the matrix of the stiffness and matrix of masses. And instead of mass, we will have mass moment of inertia in the torsional systems, and instead of linear stiffness, we have torsional stiffness. So we can solve these equations similar to the previous section. We can extract the frequency equation to obtain the natural frequencies and use the same method to obtain the mode shapes. Of course, for the free vibration, here we have this vector for the external forces, but in fact, to obtain the free vibration response, this vector must be equal to 0. So the solution is the same. We don't have anything new here, and the method is exactly the same as translational systems. Okay, we continue with another example. In this system, we want to set up the differential equations of motion for the double pendulum shown in figure using the coordinates x1 and x2 and assuming small amplitudes. Find the natural frequencies when m1 and m2 are equal to m and L1 and L2 are equal to L. Here, clearly we deal with a system with 2 degrees of freedoms. You can consider theta 1 or theta 2 as the 2 degrees of freedoms. But here in this example, we want to use x1 and x2 as the degree of freedoms. This is the x1 and this is the x2. As you can see, x1 and x2 are related to theta 1 and theta 2. I mean, x1 is equal to L1 times by sine theta 1, L1 times by sine theta 1. And if we assume that theta 1 is small, we can substitute sine theta 1 with theta 1. So for the small value for the theta, x1 is equal to L1 theta 1. And for the x2, again, we can write a relation between x2 and theta 1 and theta 2, which is equal to L1 sine theta 1. Okay, this length for x1, x2 is equal to x1 plus L2 sine theta 2 plus L2 times by sine theta 2, or again, if theta 1 and theta 2 were small, it's equal to L1 theta 1 plus L2 theta 2. So the point is here, if you want to extract the equation of motion, for example, assume that I will give you this problem in the exam and I will change the coordinate system and I ask you to solve this system and extract the equation of motion for the theta 1 and theta 2. I mean, this time you need to consider the theta 1 and theta 2 as the general coordinates in your equation of motion. So you need only substitute for x1 L1 theta 1 and for x2 L1 theta 1 plus L2 theta 2. I mean, x1, for example, double dot will be substituted by L1 theta 1 double dot, or x2 double dot will be substituted with L1 theta 1 double dot plus L2 theta 2 double dot. So you can find the equation of motion for a system for any set of the degree of freedoms. Or you can, for example, you can obtain the coordinate system, the equation of motion for y sub 1 and y sub 2, which y sub 2 can be, for example, the vertical position of mass m2. And again, you can find the something similar to these relations for x1, x2, and theta 1 and theta 2. You can find a relation between y sub 1, y sub 2, and theta 1 and theta 2. Okay, so no difference. But here in this specific case, we want to obtain the equation of motion for x1 and x2. So let's use the Newton's second law and plot the free body diagram to extract the equation of motion. So we will have two masses, and we can write the Newton's second law for each of them. For the first one, the mass m1, if you plot the free body diagram, we will have a tension T, and also we have another tension, which, for example, we can call it T1. Also we have the weight, we have the weight W1. For the mass M2, we have again the weight W2, and also we have the tension T, which this tension T is in fact the connection between mass M1 and M2, or the reason to coupling the equation of motion is this tension T. We can write the moment equation about point O for mass M1, and if you write the moment equation for mass M1 about point O, because this is a fixed point of rotation for mass M1, so in the right hand side of the equation we only have the mass moment of inertia about point O times by alpha, which alpha is the angular acceleration, or theta 1 double dot, and the mass moment of inertia for this mass m1 about point O, because this is a particle, you know, the mass moment of inertia of a particle about any point similar to this point O is equal to m times by d squared, which d is the distance between the mass and the point which you are calculating the mass moment of inertia. So IO for m1 is equal to m1 L1 squared, and here m1 is equal to m and L1 is equal to L, so it will be mL squared, as you can see here, multiplied by alpha, which alpha is theta 1 double dot. And the moment about point O, here this tension T1, because pass through point O, it does not have any moment. The tension T, this tension will have two components, one horizontal component, which is T times by sine theta 2, and also it has one vertical component, which is equal to T times by cosine theta 2. T cosine theta 2 is a vertical component, and T sine theta 2. And also we have the weight W1. Here you can see all of these forces will be multiplied by their arms. For W1, the arm is this length. Let me show with another color. This is the arm for W1, which is L1 times by sine theta 1, this arm. For the horizontal component, this one, which is T times by sine theta 2, the arm is this length, and it's equal to L1 times by cosine theta 1, this term. And finally, for the vertical component, which is T times by cosine theta 2, the arm is the same as for W1, and it's equal to L sine theta 1. For the direction, here we assume that the positive direction is counterclockwise, so the clockwise direction is counterclockwise is the negative direction, So the moment due to W1 is negative, and the moment due to the vertical component of T or T cosine theta 2 is again negative. And finally, it must be equal to, as I told you, ML squared theta 1 double dot. This is the first equation. And the second equation is the, let me clear here. The second equation can be obtained from the moment equation about mass M1. We are writing for mass M2, but the moment about mass M1. This case from dynamics, you know, because M1 is not a fixed point of rotation for mass M2, in the right hand side, in addition to IO alpha, or the mass moment of inertia about point M1, of course, this is sorry, this one is, it must be M1, the mass moment of inertia of mass M2 about the mass M1, okay, multiplied by alpha. In addition to this term, we will have m times by AD, which this A is the acceleration of mass M2, multiplied by D, which is the distance between M2 and M1, which we are calculating the moment. So we can write, and here again in the free body diagram for mass M2, we have the tension T. This tension passed through this M1, so it doesn't have any moment, and only we will have the weight, which is called W2. So you can write the arm when you are calculating the moment about M1. The arm is equal to this length, and it's equal to L2 times by cosine, L2 times by sine theta to this term. And it's here, yes, W2 times by L sine theta 2. And it must be equal to, as I told you, IM1 alpha, which alpha for this case is theta 2 double dot, and multiplied by m times by L times by L theta 1 double dot, which is the acceleration or linear acceleration. So we can substitute here, and also we can write the force equation for mass M2. You can write the force equation in y direction. It must be equal to 0 because we assume that theta 1 and theta 2 are small. So we can assume that there is no motion in vertical direction, and the mass M2 will be remain in the same horizontal surface. So by this assumption, in the right hand side is equal to 0, since there is no motion in y direction, so there is no acceleration. And we can conclude that W2 is equal to T times by cosine theta 2. Okay, here the vertical component of T, which is T times by cosine theta 2. This angle is theta 2. So this is equal to T times by cosine theta 2. And again, as I mentioned in the first slide, because theta is small, so sine theta can be assumed is equal to theta. From the Taylor expansion, we can use this assumption, and cosine theta is approximately equal to 1. So W2 is equal to T. Okay, so from here we can conclude that W2 is equal to T because cosine theta 2 is equal to 1. And also here, if you substitute for sine theta, theta, and for cosine theta, substitute 1, you can extract these two equations from the first and second equation. This is the first equation, and this one is the second equation. From these two equations, you can conclude these two equations. And now from the first slide, as I told you, you can write that x1 is equal to L theta 1 and x2 is equal to L theta 2 plus x1 or plus L theta 1. So you can write, instead of theta 1, you can substitute x1 divided by L, and for theta 2, you can substitute x2 minus x1 divided by L. And also W1 and W2 are equal to mg. Now we can simplify these equations and write in matrix form. As you can see in the matrix form, the first equation can be simplified in as the first one, and the second equation can be simplified in this form. So in the matrix form, you can extract the mass matrix and the stiffness matrix. As you can see, there is no spring in this system, but if you extract the equation of motion, we will have the stiffness matrix. The next step, we need to, because here we have a vibrating motion, so in fact, despite there is no spring, we have the stiffness matrix. So the next step, we need to solve this equation to obtain the natural frequencies and mode shapes. So for this purpose, we need to consider the response in harmonic form. We can assume that xit, which I is equal to 1 and 2, is equal to uppercase xi cosine omega t. So if you substitute in the equation of motion, you can write that we will have minus omega squared multiplied by matrix M plus matrix K, which is the stiffness, multiplied by the vector x1 and x2 multiplied by cosine omega t is equal to 0. So the determinant of this matrix, the coefficient matrix, must be equal to 0, and we can form the characteristic equation, which is this equation. Again, instead of omega squared, you substitute alpha, for example, and you can solve and obtain omega 1 and omega 2. And by solving this algebraic equation, you can obtain the natural frequencies for your system. The first natural frequency is this term, 0.765 multiplied by a square root of J divided by L. And the second natural frequency is 1.847 multiplied by square root of G divided by L. And now if you substitute into this equation here, in this equation, omega is equal to omega 1, and simplify this equation, you can extract that x1 is equal to 0.41 x2. And for the second one, if you substitute omega is equal to omega 2 and simplify, you can extract that x1 is equal to minus 2.41. So you can see we extract two natural frequencies and two mode shapes. For the first mode shape, as you can see, x1 is equal to about half of x2. It means that if you plot the first mode and consider that x1 is, assume that, for example, x2, sorry, because x2 is equal to 1. So if we assume that this length is equal to 1 unit, the x1 is about half or 0.41 of this unit. So this is the first mode shape, and the second mode shape can be obtained in the blue one. If you see here, again, if we assume that this is the unit, or x2 is equal to 1, this is the unit, x1 is equal to minus 2.41. Of course, my scales are not suitable here, it's not proper, but it will be minus 2.4. Of course, it must be more than this, and maybe it will be located here. It's not, the scalar are not correct, okay, but it will be in the negative direction. So this is the mode shapes and the application of the mode shapes. We can predict the configuration of our system when it's excited with the first or second natural frequency. Okay, so these are the mode shapes for this system. Okay, and we will discuss the coordinate coupling and principal coordinates in the next section. Okay, thank you for your attention.